Introduction to Single-Phase AC Circuits for Phase 4, RLC Circuits, Part 2. R for resistive, L for inductive and C for capacitive. All alternating current circuits contain these three components, and they are known collectively as Z, or the total impedance in a circuit. Today we will focus on the resistive and capacitive parts only, which is the RC circuit, without any inductors, and learn how to answer questions asked in your exam. We looked at RL in the previous video, and in a later video, we will combine all three aspects of RLC. Now we will do them separately to learn the basics to make the exam grade questions easy later. First of all, what is a capacitor and why do we need to learn RC and RLC circuits? If you can remember from Phase 2 and your Phase 4 electronics class, a capacitor is basically two conductive plates separated by a dielectric material, which stores and discharges an electric charge. This is beyond the purview of this, which will focus mainly on the maths questions to know and understand for the exams. To learn further about the operation of a capacitor, inductor, or indeed resistor, I highly recommend this channel, known as the Engineering Mindset. It is an incredible resource for anyone involved in the electrical game. Link in the description. Why do we need to know about this anyway? Well, capacitors can do amazing things for us in AC circuits. In industrial settings such as factories, which have many machines using motors such as conveyor belts, will have highly inductive loads, making the current lag behind the voltage and causing power loss. This power loss costs a lot of money to the owner of the factory, as the electricity provider will charge increasing penalty charges the worse the power loss is. We can fix this by using capacitors to drag the current back in phase with the voltage, because RC circuits do the exact opposite of RL circuits where the voltage lags the current. As an electrician, your job is to install these capacitors. As an engineer in the future, you will design the capacitor banks. Remember civil. CIV. I, or current comes before V, and therefore we can say that current leads voltage in the waveform in RC circuits. Here at the top is a waveform example of a purely resistive circuit. The voltage and current are perfectly in phase with one another and gives us perfect power factor. Power factor will be explained in maths questions of the exam shown in a future video. At the bottom is an example of a purely capacitive load with no resistance. The current is leading the voltage phase by 90 degrees. RC circuits have both a resistive load and a capacitive load. Loads can be considered devices which draw current. The RC circuits can be in series or parallel, or both series and parallel at the same time. Today we will focus only on RC series and RC parallel questions. Here are examples of both shown on screen now. As you can see, the capacitor is represented by two vertical lines separated. RC circuits are a little more tricky than RL circuits. This is because capacitance is measured in farads and they usually are measured in microfarads, nanofarads, or picofarads. They look like this. Looks confusing, right? Don't worry, I will show you an easy solution for these so they will be no problem to you. In our exams, we will almost certainly get a question in microfarads only, which also makes it simpler. Let's start with RC parallel example questions. Complete these with the video. Pause the video as you need or rewind if necessary. Question 1. Calculate the current taken by the supply, meaning total current in the circuit. R equals 115 ohms, C equals 35 microfarads, and the potential difference, or voltage, is 240 volts at 50 Hz. Draw out the circuit as always, to better visualize the question. Here are the formulas you will need. To get the total current, we need to get the current across the resistor, IR, and the current across the capacitor separately. Firstly, to get the current across the resistor, IR, is easy. We just use Ohm's law and plug in the numbers as shown on screen. IR equals 2.08 amps. Next, we'll need to change the value of C to ohms in order to find I total. Just like before in RL circuits, where we used the inductive reactance formula to get this value. Now we will use the capacitive reactance, or XC formula, which is shown on screen now. It is a little different to the XL formula, but just as easy once you know the formula, and just enter in the numbers for your calculator. Remember to show all your work in the exam and write down every step. This can get you extra marks even if the answer is wrong. Now we can find XC. Plug in the numbers as shown. As mentioned before, to put microfarads into the question, we simply enter the value for C. In this case, C equals 35 microfarads. So we enter 35 and for micro, we just enter multiplied by 10 to the power of minus 6. Do this every time for micro and your calculator the rest. For example, C equals 47 microfarads, we would enter 47 multiplied by 10 to the power of minus 6 into the calculator. It is that easy. For nanofarads, which very rarely if ever gets used in an exam, we multiply the C number by 10 to the power of minus 9 instead of minus 6. That is all the difference there is. Now we have values for XC, we can find the current across the capacitor using Ohm's law, just like we did with the resistor at the start of this question. Enter the numbers into this formula and you should get an answer of 2.63 amps. Now we can find IT, or I total as the question asks using this formula. The answer is 3.35 amps taken by supply. Question 2. Determine total current. When R equals 75 ohms. C equals 30 microfarads. Potential difference, or voltage in other words, is 200 volts AC at 100 Hz. Draw out the circuit. Again, we start by finding the current across our resistor using Ohm's law, because it is easy. Plug in the numbers like so, and you get an answer of 2.6 amps at IR. Now we find our capacitive reactance, using the formula for XC as shown. Enter in your numbers, remembering that C is written in as 30 multiplied by 10 to the power of minus 6, because it is microfarads. XC equals 53.1 ohms. With XC discovered, now we can find IC, the current across the capacitor using Ohm's law. Just like with IR, fill in the values as the formula asks. IC equals 3.8 amps. Finally, we can find IT, total current. Using the formula shown, and enter in the newfound numbers. IT equals 4.6 amps. Sometimes we can get lucky and the question can already give us the value for XC, and therefore we have one less step to take to find the total current across the capacitor. For example, question 3. Find the total current of this circuit. R equals 70 ohms, XC equals 212.2 ohms, PD, potential difference aka voltage, is 100 volts at 50 Hz. Draw out the circuit. Using Ohm's law, we can find IR and IC easily as shown. Put in the numbers. IR equals 1.42 amps. IC equals 0.5 amps. Now we can find IT using the formula again as shown. IT in this circuit equals 1.5 amps. Now we will move on to RC series example questions showing how voltage drops occur in these types, while current will be the same throughout. We will be asked to find either the supply current or the voltage across each component, or both. We will do examples of each. Question 1. Calculate the current flowing in the circuit. R equals 8 ohms. C equals 74 microfarads. U equals 240 volts at 50 Hz. Draw out the circuit. As the formula for IT and RC series questions is IT equals U over Z, we need to find the value for Z, or impedance. Firstly, we need to convert the value of C into ohms by finding the XC, or the capacitive reactance in ohms, as shown. XC equals 43.01 ohms. Now we can find Z using this formula. We can now show that Z equals 43.75 ohms. Now using the IT formula of Ohm's law triangle, we can show that the supply current, or IT equals 5.5 amps. Question 2. Using the same figures as question 1, calculate the voltages across each component. R equals 8 ohms, C equals 74 microfarads, U equals 240 volts at 50 Hz. XC equals 43.01 ohms. IT equals 5.5 amps. Draw out the circuit. Then we find the voltage across each component, UR and UC individually. UR, or voltage across the resistor component, is as follows. Enter the values into this formula. UR equals 44 volts. Repeat for UC, or voltage across capacitor. UC equals 236 volts. We can prove these figures are correct in this example. To prove it, we can find the supply voltage mathematically, and this should match the supply voltage given in the question. To find the total supply voltage, or UT, we put our answers into this formula. UT equals 240.06 volts, which is what we get given in the question. Question 3. Calculate the supply voltage. R equals 10 ohms, C equals 100 microfarads, IT equals 10 amps and a frequency of 50 Hz. Draw out the circuit. To get the supply voltage, first we need to find the voltages across each component. First, using Ohm's law, we can easily find UR, the voltage across the resistor. Plug in the numbers into the formula as follows, and we get an answer. UR equals 100 volts. To find the voltage across the capacitor, we need to find the capacitive reactance, or XC. Plug numbers into the formula as it asks, and you should have an answer as follows. XC equals 31.83 ohms. Now we can find the voltage across the capacitor. UC equals 318.3 volts. With UR and UC discovered, we can now find out the supply voltage with this formula. That concludes RC parallel and RC series. In a later video, I will give plenty of example questions for you to practice with answers provided at the end. For now, try doing the questions in this video also by pausing the video before the answers are given. The more you do, the easier they become. In the next video, we will look at RLC series and parallel questions. When we learn from the previous video and this video, we just combine our knowledge from them and combine them for RLC questions to make it easy. Cheers, and see you on the next one.